High-speed rail is usually defined for new lines as having speeds in excess of 250 kph and on existing ones greater than 200 kph. Whilst it is seen as a feature of modern railways, it's actually been around since the 1930s. Even in the US, after the Great Depression, which caused a huge loss of business for the American railroads, high-speed rail was seen as the way to get people back onto the trains and make them profitable. In the mid-1930s, the Pioneer Zephyr Streamliner was one of the first to incorporate a lightweight aerodynamic stainless steel body, Jacobs bogies between the rail cars, and used a two-stroke diesel-electric power plant. It ran on the Chicago, Rock Island and Pacific Railroad and could reach up to 185 km per hour but averaged 124 in service. One of the first in Europe was the DRG class SVT 877 Hamburg Flyer, a two-car streamlined diesel-electric that ran on the Berlin to Hamburg line from 1933 till the outbreak of war. It travelled the 286 km route in 138 minutes at an average of 120 kph, although it could reach 160 kph, a time that took a further 64 years before it was matched by a modern intercity express in 1997. In 1939 in Italy, the electric FS class ETR 200 averaged the 305 km journey from Florence to Milan at 165 kph and set a new record of 203 km per hour. The year before, in 1938, the British Mallard steam locomotive achieved the same speed as the fastest steam train, a record which still stands. But the Second World War effectively stopped all high-speed rail development until the 1950s, when the French National Railway SNCF began testing the new Alstom CC 7100 electric locomotive. This achieved 243 kph, pulling a full train on standard tracks in 1954, and then in 1955 a CC 7107 reached 331 km per hour. Meanwhile in Japan, the post-war economy was booming, and so was the need to transport people between the densely populated centres of Tokyo and Osaka, also known as the Tokaido Belt. The existing rail system was becoming overloaded, so the idea of a new high-speed railway was brought back from the 1940s. Japanese engineers from the Japan National Railway attended the Electrotechnology Congress in Lille, France, during a 6-month visit to study the high-speed rail work being carried out in Europe. They left with many ideas, and these would be adapted and used to build the Shinkansen or bullet train, the first truly integrated high-speed rail network in the world. The bullet train was the nickname given to a project discussed in the 1930s, and then the Shinkansen was the formal name used in the 1940s as a high-speed rail system that was envisaged running from Tokyo to as far as Beijing in China, through a tunnel to Korea, and then on to as far as Singapore. Some of the original tunnels dug for that in Japan were later used for new Shinkansen lines. The initial construction of the fully electric service started in 1958, and by 1964 the O series with the classic bullet-shaped noses started regular services, running at up to 210 kph, and were a source of great national pride. The aerodynamic bullet look was created by Tadano Miki, who was a plane designer in the war, and had designed the single-seat rocket-powered Yokosuka MXY-7 kamikaze planes used by the Japanese in the latter part of World War II. By comparison, at the same time, the UK, the country which had invented the railway, was transitioning from steam to diesel and was still regularly running steam trains up until 1968. In order for the Shinkansen to run at full speed, it has its own dedicated lines, using the standard gauge compared to the existing narrow gauge. This allowed greater stability at high speed and no slow commuter or freight traffic to be in the way on most routes. The traditional tracks were also an issue. For high speed, they need to be precisely aligned and the curves need to be shallow and banked. For this, continuously welded rails are used, and it's often easier to build a whole new track than it is to try and upgrade an existing one. This has contributed to it being the safest railway system in the world, with no fatal accidents since the service started, despite it carrying over 10 billion passengers, or the equivalent to 1.4 times the entire world population in that time, and having only 2 derailments whilst in service, and one of those was during an earthquake in 2004. Because of the threat of earthquakes, the Shinkansen has a sophisticated detection system that picks up the much faster P or primary shock waves of an earthquake and immediately shuts down the electrical supply and applies the brakes of any train in the affected area, before the much more damaging but slower S or secondary shock waves hit. This is believed to have saved many lives when the 8.9 magnitude earthquake and tsunami struck in 2011, when many of the Shinkansen in the area were travelling at well over 200 kph. In order to get the amount of power required, the voltage of the overhead lines was up from 1500 volts DC to 25,000 volts AC. This allowed the overhead cables to be run thinner and lighter as the current increases as the voltages step down in the train. New self-adjusting pantographs allowed a reliable supply of electricity at high speeds with less wear and tear. Instead of a power car or locomotive at each end, the Shinkansen has electric multiple units, with each axle on every coach being powered, effectively giving it all-wheel drive. This gives it greater acceleration on the many stops of the journey, with less weight per axle, reducing the amount of wear on the tracks. It also allows the Shinkansen to negotiate tighter curves with a radius of 2,500 metres compared to the 4,000 metres of the TGV. This greater load spreading also allows trains to carry more passengers per metre of train length than any other high-speed train, meaning they can move more people per train, with each train normally having up to 12 cars, rising to 16 with later models. As time went by, the speed of the Shinkansen increased to 320 kph. This presented a problem when going through tunnels, and the Japanese tunnels were also smaller in diameter than other rail networks around the world. This created a sonic boom as they exited the tunnels, so the noses of the trains became much longer to help spread the shockwave along the front of the train and reduce the effect. After the success of the bullet trains in Japan, the Germans and the French in particular concentrated on their own high-speed rail systems. The TGV, which was built by Alstom and means a train à grande vitesse, was originally designed to run with gas turbine engines from a Super Freelon helicopter, driving alternators which generated the electrical power for the motors. The prototype TGV 001 covered nearly 1 million kilometres during testing and had a top speed of 318 kilometres per hour, still a record for a non-electric train. The TGV followed a more conventional 2 power car layout, one at each end with coaches in between, and used Jacobs bogies as seen on the Hamburg Flyer and the Pioneer Zephyr. This is where one wheelset or bogie is used between 2 rail cars instead of one at the end of each rail car. This makes the train set lighter and more rigid. This was quite different from the Shinkansen all-wheel drive and the 2 wheel sets per car, and allowed the TGV to be more stable at high speed due to a more rigid layout, but it also meant that the minimum turn radius was 4,000 metres. It also means that the cars can't be separated without visiting a specialist engineering depot, unlike the Shinkansen, which can be split like a normal train. However, when the oil crisis of 1973 hit, the cost of fuel for the turbines rose dramatically, forcing the design team to switch to a new all-electric design like the Shinkansen. This actually suited the French and to a lesser extent the Japanese quite well, as both had a high proportion of their electrical supply generated by nuclear power, which insulated them from the oil price up until the Fukushima nuclear accident in Japan of 2011. The first all-electric TGV prototype, called the Zebulon, ran in 1974, and by 1981 the first purpose-built high-speed rail line and TGV were available to the public between Paris and Lyon, and went on to set a new speed record of 380 km per hour. Due to the speed that both the TGV and the Shinkansen travel, it was deemed that trackside signals would be approaching too fast for the drivers to react in time. So both use automatic braking systems, so that if one train slows and the drivers of the ones behind don't react within a set distance, the brakes are automatically applied. This allows trains to run at closely scheduled intervals without bunching up like road traffic does when one vehicle unexpectedly slows. Wherever a high-speed rail line has been established, the air traffic between the same 2 points has decreased dramatically, as it's much quicker to get on and off of a train compared to a plane, and the stations are in the population centres rather than being away from them, even though the plane is much quicker once flying. But there is a limit to this. In Europe it's 3 hours and in Japan it's 4. If the journey by train is longer than this, then the balance tips towards air travel and away from the train. In the early 2000s, Alstom started work on the next stage of the TGV to develop the AGV, or Automatrice à Grande Vitesse. This adopted a similar principle to the Shinkansen of a distributed power system and doing away with the powered locomotive ends, yet keeping the Jacobs bogie layout. This and an all-new aluminium body and new permanent magnet motors reduced the overall weight of the train considerably. In 2007, a TGV duplex, that's a double-decker railcar version using the AGV power setup, set a new speed record of 574.8 km per hour. Though in service, the AGV, which was sold to the Italian National Railway, would run at up to 350 km per hour. The Chu Shinkansen L0 series maglev in Japan has recently retaken the high-speed record with a run of 603 kph set in 2015. It's difficult to say if one is better than the other because they are a result of how they were designed for what are really quite different geographical areas and operational goals. But both types are now being exported around the world and been adopted from the US to China, which is probably the best endorsement they could have. Building the high-speed railways of today has taken a huge amount of technology, not only in the trains themselves, but in the tracks, the power systems and the computerized routing, something that needs knowledgeable people with the skills to be able to bring it to completion. Brilliant, the sponsors of this video, is a problem-solving website that can help you develop those skills by breaking down problems into small, easy understandable parts and then putting them back together to show the overall solution. You can download any of their dozens of interactive courses through the mobile app, with more being added each month. You'll be able to solve fascinating problems in math, science and computer science no matter where you are, even if your mobile internet connection is not the best. There are loads of great totally interactive courses. Use computer science to work out which stations a train should stop at, or classical mechanics to determine how long it will take for a train to decelerate to a stop from a particular speed, and many more to boot. So if you want to support Curious Droid and get unlimited access to all of Brilliant's in-depth math and science courses, you can head on over to brilliant.org/CuriousDroid to get 20% off of their annual premium subscription.